So, good afternoon. We're live. Welcome to the second day of our workshop on Copernicus and the Green Deal. We have a great number of exciting speakers lined up for you today. We're going to have an introductory session just now with a few Slido questions. We will come to those in a minute. And we will follow that with two keynote presentations. We will have a session on climate at about 1:30, followed by clean energy at 2:15. Then we break briefly for coffee at 3, and we continue with a session on mobility as well as zero pollution at 3:15. And we finish the day off, we round it off with a panel discussion at around about 4 p.m. wrap up and end the day at 5 European time. So I'm Eric Anderson, and I work at DG DEFIS at the European Commission in the unit that runs the Copernicus program. So as I said, we're going to start the day with an interactive poll on Slido. So if I could have the organizers please help us bring up the instructions for Slido. So you can see on the screen now, there are various ways of connecting to Slido. You can use the QR code on the screen with the camera on your mobile phone, for example, and that will take you straight there. Alternatively, if you go to a browser, type in slido.com, you will be asked to fill in the code to access our corner of Slido, and that code is Copernicus Green Deal as one word. So that will take you to the Slido questions. And should I expect those to appear on the screen as well? Right. So we have 3 questions altogether. 2 of them are of this form, so multiple choice, and you simply choose one of the answers. And the remaining question is of the type of a word cloud. So we focus on the current one that's up at the moment. How would you rate the relevance of Copernicus for the implementation of Green Deal actions? Of course, those of you who attended the session yesterday will have you will have information to base this on. If you didn't attend yesterday, you may have own pre-existing experience of Copernicus and the Green Deal that will guide your answer. So we'll leave that question up for up to a minute for participants to respond. Some of you may still be finding your way to the Slido question, so I will leave it up for a minute. So to those of you who are just joining, this is right at the start of the session, the workshop on Copernicus and the Green Deal. And we are starting with an introductory part where we're going through just a couple of Slido questions. And you can see on the screen now a QR code that you can use to access Slido, and you can also access it directly via the QR code or via browser to slido.com using the code word Copernicus Green Deal to access our corner of Slido. Great. We have a very strong majority of positive responses to this, the first question. How would you rate the relevance of Copernicus for the implementation of the Green Deal? Okay, I will just close this first question at this point and move on to the second one. If you could bring us to the second question, please. So this will result in a word cloud. What do you see as being the key Earth observation information product for Green Deal implementation and monitoring? So this can be a type of observation, name of a data product that you are either using or are aware of as an important source for Earth observation for Green Deal implementation and monitoring. Again, I will leave this question up for up to a minute while the answers are coming in. Okay, I'm going to repeat myself for those who are just joining us. This is the second day of the Copernicus and the Green Deal workshop, and we're starting with a Slido poll, interactive poll, and we're creating a word cloud to the question, what do you see as being the key Earth observation information product for Green Deal implementation and monitoring? The instructions how to access Slido is there on the left of the screen. And it's worthwhile connecting Slido not only for this poll, because we're also using it throughout the session for the question and answers. Okay, I think we're coming to a conclusion on that one. It's the Sentinels, the family name for the satellites of Copernicus. It's the CO2 emissions for, obviously monitoring our progress towards decarbonization in Europe, greenhouse gases generally, and Reanalysis, climate reanalysis are the big players here, plus many others. Thanks for that. We move on to the third and final question of this type in Slido. This is multiple choice, and this is whether you know sufficiently well how to find, access, and exploit Copernicus data and products. And you have multiple choice. Okay. There is a bit more of a spread here. We had one of the questions yesterday that came up was about user support for users of data. And we were able to respond to that in writing yesterday. And those replies will be made available also after the event. But the one on user support, I think, was an important one because they gave us the opportunity to point the participants yesterday to the various user support functions that exist within Copernicus, run by the services themselves, and training material as well. So thank you. We will close the Slido poll at this point and move gradually to the first session. I should say first that while my colleague Ivan was chairing yesterday, I was in the background moderating the flow of questions from participants in Slido, and I just want to take this opportunity to point you again as participants and speakers to the interactive question and answers that we are running in parallel. So today, as I said, we're focusing on climate, energy, transport, air pollution, as well as the monitoring of greenhouse gases. And we're starting today's presentations with two keynotes. The first one will be presented by Geert Manhout from JRC, where she is the head of the bioeconomy unit. So Geert, it's over to you.
Thank you.
Welcome.
Thank you and good afternoon. Do you hear me? Do you hear me well?
Yes, certainly.
Okay, thank you, thank you. As a big fan of Copernicus, it's of course my pleasure to talk about this user-driven program and the uptake of Copernicus and Earth observation in the European Green Deal policies. Now, where did we start from? In a certain way, Copernicus did go already a long way. So if I go to the next slide, please. We have, and probably you remember, seen an increased effort on climate policies with the big Paris agreement, a landmark agreement. Also, that came together with Agenda 2030, which was boosting a lot of SDG data. And that has been paving us the way as well in the Commission towards quite some regulations and policies, in particular on climate. Over the same period, we have seen as well a lot of sentinels up in space, starting to produce a growing, exponentially growing amount of information that can be used for this environmental monitoring, and in particular as well, monitoring for climate regulation. And I would like to mention in particular that the LULUCF regulation is one of the first regulations where really Earth observation and Copernicus data are mentioned as a real need for implementing the regulation. Let us go to the next slide, please. Coming to climate, I would like to illustrate with two things how Earth observation is so important. So on the left-hand side, you see the RED initiative, the reducing of emissions through deforestation and forest degradation. Over the different continents, we have been able, using Landsat and now recently also Sentinel data, to see deforestation happening, and that can be traced back over the over a long time period, more than 20 years. 30 years, sorry. And that is providing quite a lot of input, and we will see later as well in a recent regulation proposal on deforestation-free products traced. On the right-hand side, you see the LULUCF with a certain graph here represented. So we know from LULUCF inventories that are reported that we have there high uncertainties. What came as well apparent is when you look as well at geospatially based models, that you find as well gaps that are not captured when looking only at reported inventories purely based on statistics. And so also here we see the real need for using Earth observation data for making more benefit. But let me bring you further to the timeline up to the current von der Leyen Commission in the next slide, please. You see that we have been working hard with a lot of regulations on climate policy, and that culminated in the Fit for 55 package, where there was as well the revised LULUCF regulation, even a strengthening of the monitoring of the LULUCF. You find as well the EU forest strategy, also there with monitoring needs. And we are currently working on the nature package, which partially is already done with this regulation on deforestation-free products trade, but and a communication on sustainable carbon cycles, but also with the nature restoration law proposal that now has been postponed because of the Ukraine conflict. In all these regulations, we see an enormous importance of monitoring for implementing these regulations. And so we see as well as many of them talk about biodiversity, ecosystems, forests, which are very different in the north than in the south of Europe. Therefore, it is so important to take up as well geospatially based data. Now, if we go to the next slide, you see here for Europe what one of the assessments can be by looking into Earth observation data. This is a Nature paper that hinted towards an increased harvest of woody biomass over European forests. Now, this increased use can have different drivers, and that is, of course, then to be seen at the other side. We know that woody biomass is used and for renewables as well as for carbon sink. There is as well an increase in the salvage logging. So there are many different reasons for that. But very important is that it has raised enormous the attention of the woody biomass and as well the link of using Earth observation data for harmonizing in a certain way across all the member states. If we go to the next slide, I would like to mention in particular as well that the revised LULUCF regulation really brought a kind of a revolution in climate policy. The second one, first we had of course the emissions trading system, and then there was a revolution with the effort sharing that was as well taken up. Now in the third place also LULUCF is taken up, and the whole AFOLU will need to contribute to the climate targets. And in the regulation it's really mentioned that AFOLU needs to be climate neutral by 2035. That means monitoring a sink and monitoring a source, the source of the agriculture and the compensation by the sink of the forest in simple terms. Of course, we talk about different gases, so also quite some challenges, and that definitely will contribute further to what will be taken up in the CO2 monitoring program of Copernicus and RECAMS. If we go to the next slide, please. Outside Europe, we see that Copernicus, there is not only a red component that is now flowing into the global land component of the Copernicus Land Monitoring Service, but we want to have as well an EU observatory platform for deforestation, forest degradation, and associated drivers that looks at data from Earth observation and combines it with trade statistics. And it's exactly this combination of different types of data that brings the richness of our understanding and our science forward in a certain way. And also our policies forward. And we would like to do this together with the scientists, and so we are as well looking at this forest science partnership there. Next slide, please. On the nature restoration law, we again will use an indicator that is based on Earth observation, forest fragmentation. That is one of the first indications that there is degradation. And also here, geospatially data needs to be taken up to be really give some indication on the connectivity that is so important for biodiversity conservation. As such, I would like to conclude with the next slide. that gives an overview first. Yes, the time is ripe to make use of Earth observation evidence based on data and based on models for EU bed regulation and policy implementation. And in the next slide, I think it is very enriching to overlay data, to have this integration of information, hybrid modeling, and especially now as competition for land is by different activities is very, very high. And we need to have our policies taking this into account. The concluding remarks you find in the next slide, which just summarizes what I've said before. Thank you very much.
Thank you, Gret. Thank you so much for setting the scene for today's sessions, today's workshop, and tying this in with the important regulations in place and the Fit for 55 package that was recently introduced. So I will move to our second speaker, our second keynote, to be given by Samantha Burgess. Samantha is the Deputy Director of the Copernicus Climate Change Service. Welcome, Samantha, and over to you.
Thank you, Eric. Can you hear me well?
Yes, go ahead.
Great, thank you. Next slide, please. It's always such a benefit being on the second day of a conference when we've heard so much information about how important climate insights are, not only to deliver the Green Deal, but also to deliver the Sustainable Development Goals. And the reality is that climate insights have never been more important. We saw in the World Economic Forum report that was published a couple of months ago, 3 of the top global risks were focused on climate action. So climate action failure, risk of extreme weather, and risk of biodiversity loss. The figure on the left-hand side shows the level of change that we've observed in the Northern Hemisphere over the last 70 years. And you can see the gradual colors change from blue to red, showing how much our planet is warming, particularly in the Arctic region and in the Northern Hemisphere. Next slide, please. And so this very short keynote today is to really give some highlights of what the Copernicus Climate Change Service has achieved in the last few years of operation, and also what we will deliver over the next phase of the Copernicus program going out to 2028. So apologies for the very busy slide. There's a lot of statistics on this slide, but it's really just to give you some insights of the level of impact that C3S has had in the few short years since it's been operational. And 2 of the key features that I'd really like to highlight is the impact the C3S has had in climate assessments globally. So in the IPCC 6th assessment report, Working Group 1, that was published in August last year, C3S was presented as an exemplar climate service. And the Reanalysis, so it was great to see Reanalysis popping up in that Slido poll a few minutes ago. Reanalysis in ERA 5 was cited over 200 times within the report. And indeed, our contribution to scientific development, one statistic that we can touch upon directly is the paper by one of my colleagues, Hans Hirschbach, which was published not even 2 years ago. It's already been cited over 2,500 times. And you can see the difference in the numbers here from when we did the screenshot versus when I sent the slide deck through. So there's an extra 100 citations every 2 weeks or so. So ERA 5 is this phenomenal resource for the scientific community to understand our past climate. Next slide, please. And really the way we do this is C3S is at the nexus of providing transitioning climate data in terms of all different types of observations. So not only from satellites, but from in situ observations from the land, from the sea, and from the air. transferring those petabytes of data and information into kilobytes of meaningful information for society, for legislators, for businesses to really take direct action. The way we do this is through our climate data store, and we already have over 123,000 direct users of the climate data store, and then many, many more institutional users. That expands that reach. Next slide, please. So in terms of the types of data that C3S provides, really we are covering the entire spectrum of climate information that is required for the Green Deal, for climate adaptation. So we cover information from the past, both in terms of observations and in terms of our Reanalysis products. We also cover the present in our climate predictions and seasonal forecasts. And we also include the same data that was used in the IPCC report, so the latest CMOP6 climate projections, so that we can understand what choices we have to make as society to get to this climate neutrality by 2050. Next slide, please. And one of the things that many people struggle to understand is the complexity of the climate system. So this is a representation of the Global Climate Observing System, which has defined 54 different essential climate variables. And of those 54 essential climate variables, C3S has almost 30 available within the climate data store. Many of these are directly from satellite observations, but we also support this package of 22 satellite observations with ones that come from Reanalysis, from ERA 5. Next slide, please. And in terms of understanding and observing our climate system, this means that we can monitor the climate system. So as part of our monitoring, we monitor regularly, so monthly and annually, on what those changes are and how the different climate indicators that make up the impacts of climate change on our planet, how they're changing through time. And this enables society to understand both the long-term trends and the interannual variability that we see in temperature changes in particular. Next slide, please. So in terms of Reanalysis, I think many people in the audience are familiar with this, but what it does is it combines the latest numerical weather prediction model with observations, and it assimilates that data to create a map without gaps. So ERA 5, the product that is our most used product within C3S, it's a 30-kilometer resolution all over the world that provides over 250 different variables in every single grid box. It goes back to 1950 and it's close to real time, so you can really understand the climate that you're interested in for your location and understand the climate changes that have occurred in the past. And this enables people to understand the future risk and future exposure to future climate change impacts. In addition to this global product, we also have a series of regional products. I don't have time to go into them today, sadly, but these include both the Arctic Reanalysis, which is much higher resolution. It's 2.5 kilometers. We've got a European regional reanalysis, which is 5.5 kilometers. And then we also have the ERA 5 land product, which is 9 kilometers resolution. And all of the information is available on the climate data store, and it really gives a lot of information and documentation supporting users of which product to use that is best for their purposes. Next slide, please. And what this enables us to do is to reconstruct the weather. So on the left, you see a very famous image from a NASA Apollo 7 that was taken in 1972, and using the latest numerical weather model initialized from ERA 5, we've been able to recreate the weather system for that day within the model. So you can see that there are some differences between the original photo and the model representation, but overall you can see a huge number of similarities in the cloud structure in particular, which is really all we can look at this really zoomed out scale. But this is one of the exciting developments of ERA 6, when in the next phase of we will get to a coupled system where we'll have a dynamic ocean, the resolution will be higher, so we'll be able to reconstruct even more closely to what we have really observed in reality. Next slide, please. So moving on to one of our other products, seasonal predictions. Again, we've heard some of the uses of these in other presentations, and we really provide a multi-model ensemble where we use all of the best seasonal forecasts across Europe, not only the one from ECMWF, but also from DWD, from Météo France, from CMCC and from the Met Office. And then we have several other seasonal forecast products provided in kind to provide this multi-model ensemble. So the ones provided in kind are from NOAA, from Canada, and also from Japan. And later this year, we will be adding on the Bureau of Meteorology in Australia as well. And this really enables us to provide a range of different products. So over on the right-hand side here, you can see a couple of graphical outputs looking at differences in precipitation for that particular forecast, and also the Nino 3.4 index. Actually, I think that's actually the Indian Ocean dipole rather than the Nino 3.4. Next slide, please. And one of my last slides is really to show how this information is then applied to society. So we have a huge number of applications where we've engaged with different sectors to understand what their needs are. And one of the most topical issues at the moment is energy security. How do we get to energy security for the climate neutrality ambitions and the net zero ambitions of 2050? And here we can see our an example of our operational energy application, where it goes through all of the different renewable energy products and looks at explorers, both in terms of the data for reanalysis, so for the past, and it also uses regional climate projections so that you could look at the particular country that you're interested in and compare what future potential there is from solar compared with hydropower compared with wind, for example. And there's a wind session later today that will showcase some of the C3S data in a lot more detail than I've been able to do here. Next slide, please. Finally, one of the really important components of making an operational service is ensuring that users can trust the data and that there's complete traceability back to the source of the data, the institutions that created that data. So we're incredibly passionate about our evaluation and quality assurance program as part of C3S, where we do independent assessments. So not we, but we, the scientific community provides independent assessments of the robustness, the maturity and the fitness for purpose of a whole range of our data products. And you can see this information available on the Climate Data Store, where through the summary information, it goes through the strengths and weaknesses of particular data sets and gives you indications of where it's considered to be a scientifically useful product, where it's considered to be robust enough for decision making, and where there are challenges associated with either the resolution or the length of the time series. So it gives that information for users to make their own choice of picking the right data set to suit their needs. Final slide, please. And thank you so much for the opportunity to give more information about C3S today. And we're available on all social media channels, so very happy to discuss in more detail. And I'd like to say happy World Meteorological Day to everyone today as well. Thank you.
Thank you, Samantha. Thank you so much. Thank you for explaining what reanalysis are. It's such a key component of climate monitoring, and it's the basis for so many products in the range of Copernicus products. And also you linked, one of the examples you showed was energy. And as you said, we will have a session on energy later this afternoon. And you also introduced essential climate variables. And I think that's a topic that our next speaker will take up as well. Our next speaker is Han Dolman. Han is director of the Netherlands Institute for Sea Research. Welcome, Han, and I can't see you on video yet. but if you're with us, over to you, Han.
I should be. Can you hear me?
I can hear you. Go ahead.
Okay. Yes, thank you for inviting us at this this meeting. What I would like to do is to say a few things about how we define the ECVs that were already mentioned by the previous speaker in GCOS, and how we evaluate them also by assessing the status of the global observing system. And then I would like to move on as an example towards the CO2 monitoring mission that is currently on the cards of Copernicus. Just to remind you that in 1992, there was the Rio conference, which you could argue was also something of a global Green Deal that established GCOS. And what GCOS does is basically guiding the planning and development of a global observing system. And that's an observing system that goes across land, ocean, and atmosphere and cryosphere. So it tries to cover the whole climate space that we know from our Earth system understanding. We don't do observations ourselves, but we try to guide the observing systems in a way that they measure according to the GCOS monitoring principles and also the ECVs that we define. Can I go to the next? So we have what we call a large value chain, in which Copernicus is one of the key players. On the left-hand side, you see that we plan those sustained observations, and making those observations sustainable is one of the key issues at the moment. A lot of the observing systems, particularly those in the ocean, are funded on short funding cycles of a few years. And what you really need for climate monitoring is long-term perspectives with the similar amount of funding. We try to listen to our stakeholders, and as I mentioned already, Copernicus is one of those bigger stakeholders, because they can define very well what is needed in terms of climate services and the further downstream applications. And we try to bring that back into the requirement definitions for our essential climate variables. And we try to then finally make that into decision making through the climate services itself. That's a full cycle of which we primarily take the part that is here in the dashed line. That's what we do. Defining ECVs is to some extent our core business. Suggesting improvements and reviewing how well they are executed is what we do. We go to the next. So these are our ECVs. You've already seen that in the previous talk. They're grouped here in the main cycles of the Earth system. So we have the hydrological cycle, carbon cycle, and the energy cycle, which involves the temperature. The key thing about why we also try to look at this from a cycle perspective is that it allows us to see how well we're able to close budgets. And of course, the carbon budget is one particular thing, but also the hydrological budget is an important, and the energy budget that basically keeps track of where we go with our current warming trends is an important issue. Can I go to the next? So again, the key definitions of an ECV are that it should be relevant for the climate system. That's a bit of an obvious criterion, of course. It should be feasible. So we're not, in a way, defining ECVs that can't be measured at this point in time, even though you might like to have a particular variable at a global scale. And the global scale is also important. We try to do that at the global scale. And there has to be some sort of an element of cost effectiveness in. Although if somebody came up to us and said, well, I'd like to spend 2 billion euros on a particular item, on a particular ECV, that's of course up to the provider of those funds. And we go to the next. Oh, that's something went terribly wrong here, I'm afraid. I'm missing a few slides. These are Philippe's slides. So can we go one back? Let's try and keep it with this one. I'll try and look, make it from my my own slides here. One of the things that I said, we look at the carbon cycle, and what we find is that the current observing system allows us to determine pretty well how much we emit in the atmosphere. It doesn't really allow us at the moment to look very carefully at the interannual variability of those measurements. And so we need to improve there. And the CO2 emission, which is currently on the cards, is one of those elements. And the thing I'd like to stress with that that mission is that measuring just one particular ECV is not enough if you really want to assess elements of the carbon cycle. So if we want to make sure the atmospheric concentration can be measured by a single satellite, that's fine. But if we really want to determine how much emissions are coming from power plants or cities or even agricultural areas, then we need also to have large information on land use change, etc. A lot of the things that Greet Manhout were talking about, and that I think is one of the strengths of Copernicus, and probably also the relevance to the Green Deal, that we're able to link these various components in a budget or carbon cycle perspective, and that allows us to make progress in understanding what's happened, but also in allowing to monitor whether reductions are being put into policy frameworks. So apologies for the fact that those 4 slides are missing for some reason. That's basically what I wanted to say.
Thank you, Han, and apologies from our side for messing up half your talk in terms of slides.
I don't know what went wrong.
I'm going to give you a few more moments to recall your thoughts, see if there's anything else that springs to mind that you wanted to cover, but perhaps weren't able to without guidance from your own slides. We actually give you an opportunity to catch up on anything else you wanted to say, perhaps.
No, I had a particular example of what we call the atmospheric fraction. So that's the amount of CO2 that remains in the atmosphere compared to our fossil fuel emissions. And that fraction is a key indicator of how well the oceans and land are still taking up carbon. And there is a fear that that fraction might go up. But some recent work that just came out last week in Nature suggests that it's actually at least stable at the moment, and maybe even going down a little bit, which is good news in the sense that the land and the ocean are still taking up a lot of the carbon that is being emitted. But the reason why I was showing that example is that without accurate data on land use change, which also provides emissions, it's impossible to really analyze that particular indicator of the carbon cycle. So that's where there's one example where a lot of the different ECVs come together, and it's very useful to have those available within the sort of frameworks that Copernicus is providing.
You're absolutely right to stress the fact that the policy goals in terms of carbon reduction are formulated in terms of net, meaning that we need to monitor both the emissions from data such as CO2M, as well as the uptake in land and ocean and changes in uptake from land and ocean. Right, so can I have confirmation from the organizers that we're ready to go with the next set of slides? I think we are. So I will introduce our next speaker, which is Philippe Siez. Siez is really a specialist on carbon monitoring, as you will see from his talk. And Philippe is a research director at LSC in France, the Laboratoire des Sciences du Climat. So Philippe, welcome, and please go ahead.
Yes, thank you very much for the invitation. I will try to share with you a few thoughts in the following slides. The next slide, please. About what are essentially the essential climate variables we have and those that we ought to have in terms of monitoring greenhouse gas emissions and removals for the Paris Agreement. Next slide, please. So in a general context, okay, we have, of course, the UN 2030 Agenda for Sustainable Development, and this will require a number of climate services, and a lot of them are relying on Earth observation data to support adaptation in different sectors, energy and agriculture, but also mitigation. And when it comes to mitigation, I think the main idea is to make the enhanced transparency framework of the Paris Agreement as effective as possible, because there are a lot of things at stake, in order to have the capability to monitor the effectiveness of mitigation action, not only in the EU, but also worldwide. And regarding the EU, of course, the critical point is to be able to have the right tools to monitor the effectiveness of the Green Deal actions. And I here think that both the low latency and high accuracy are important, because we are living in a world that is changing terribly fast. After the COVID, emissions have decreased and rebounded. And now we have an energy crisis and a food crisis. Things are changing much faster than anything we could have expected a few years ago. And decreasing the latency of information is very important. The second thing is, of course, to support the improvement of inventories for the global stocktake. The third point, where I see an important use of Earth observation, is that the kind of uncertainty of the climate projection has not been reducing from different cycles of the IPCC, in particular because there are fundamental emerging properties of the Earth system, like the climate sensitivity, which are very complex to simulate by Earth system models, which are still not well constrained. And here we have very big role for the different TCVs that were presented by Handelman to help the climate modeling community to reduce uncertainties on projections. The same is true for nonlinearities in the climate system. We know that they exist, but we don't know at which global warming level threshold they will start to be, let's say, excited, and what will be the impact. I will pass on the last two slides and take the next slide, please. So it's not the original set of slides, but in terms of mitigation, there are four main kind of data set or important variables that we want to have. First of all, we would like to have an independent top-down monitoring using atmospheric greenhouse gas concentration. It's a method called inverse model to be able to capture the changing trends of anthropogenic emissions. Right now, they are only estimated, self-reported by countries based on inventories. These inventories are accurate in some countries, but it's very important to have an independent monitoring system. The second point is that we are also asking a lot to the land use sector, the AFOLU, for removing carbon dioxide, and also reducing emissions of methane and N2O. Today, the land is a net source of greenhouse gases because emissions of methane and N2O are larger than the carbon sink. And it's also very important to work on a high spatial and high temporal resolution information about bottom-up greenhouse gas sources in the different subsectors of the AFOLU. Thirdly, we need information to support national scale emission inventory in terms of consistency, reproducibility, verification activities. And also, we need to support the Global Stocktake project, the Global Stocktake initiative of the UN, by being able to harness observation for tracking the progress at the global level of the efforts which are in all the countries, and also of the land which are not managed, which are not in the scope of the inventories, but they still contribute to the greenhouse gas balance of the Earth, and of course of the oceans. The next slide, please. I'll try to be very quick. So this is just essentially to remind you that we are not going on the right track and we need information. First of all, to assess the baseline. There was a paper produced by the Washington Post to which we contributed last year for the COP, showing that there is a big difference between so-called scientific estimate of emissions of greenhouse gases by countries and the official numbers. So making the baseline more certain, and also being in the capacity to monitor regional trends to track the effectiveness of climate policy. The next slide. This is where we are for the capability to track CO2 emissions using spaceborne measurement. We do not have really dedicated satellites. We have OCO2 and OCO3. They have been launched for diagnosing the global land and ocean fluxes, but sometimes they pass over cities and power plants. And the situation in this paper that was recently published a few weeks ago, part of the COCO2 project, is that today we are only able to capture 400 sites. And these are really snapshots. And you fly over Paris, you get a point to estimate the emission of the city, and then you have 300 days a year where with the current satellite capability, we cannot monitor CO2 emissions. The next slide, please. So in order to reinforce this capacity, the European Commission and the European Space Agency have taken the step to launch a constellation of imagers. Imagers is really the key word because they will reveal the plumes of power plants and cities, and they will allow us perhaps not to capture all the emissions of fossil fuel CO2, but at least a much larger share compared to what we're able to do with the current instruments. Those missions will be launched in 2026, and the challenge is really to get the capacity in terms of services to maximize the use of those concentration measurements to derive emission products. The next slide, please. For this, I would argue that satellites need help. They need help from information system. What we are trying to do is not just to say, well, satellites will fly over cities and they will measure their emissions. You will always have clouds and regions that are difficult to measure, uncertainties on the measurements, but we can combine with atmospheric transport model very fine-grained information about the space and time pattern emissions together with atmospheric concentration measurements. This is what we have been doing in the Carbon Monitor initiative. We have been collecting about 20,000 near real-time data per day in different sectors like power production, car traffic, and so on and so forth, mapping emissions at 10 kilometers every day over the globe. There are, of course, uncertainties in those maps, but it's an essential ingredient of an information system that will eventually combine atmospheric and bottom-up estimation. Namely, we need more dynamic, more high resolution, high temporal resolution, low latency inventories of emissions. The next slide is about methane. So we know that methane, of course, is a very strong forcer. It's also a short-lived forcer. So if we cut down methane emissions, we will see lower warming quickly. A lot of the methane is produced by the oil and gas activity, also by coal extraction and by agriculture, and it's very high up in the agenda with the Glasgow pledges, where more than 100 countries collectively decided to cut their methane emissions by 30%. There is the IMEO initiative of the UN, and of course the EU methane strategy. The next slide shows also that the next slide, please. Yeah, that current satellites, in particular Tropomi, have been very successful at being able, for the first time in the world, at capturing the signal of very large emitters. You can see a series of images, and you can see plumes from very large emitters, mainly maintenance or accidental events, that can be analyzed with dispersion model. And the next slide is showing the result of this. It's a paper published in Science a few weeks ago, where we found that about 10% of the methane emissions are coming from ultra leaks, ultra emitters, very large events, more than 20 tons of methane per hour emitted sporadically. And those emissions have not been censored, they have not been surveyed before by inventories, and clearly fixing them, as we analyzed in that paper, would have a negative cost because you can recuperate the resource, and also it will have huge benefits for air quality and climate. So this is typically a low-hanging fruit for climate mitigations, and we can also use other satellites like Sentinel-2 and Prisma to essentially improve the detection level of leaks, to go now from 20 up to 1 or 2 tons of methane per hour for leaks, in particular in the oil and gas sector. The next slide is about the land use sector. The next slide, please. It's also a very important sector. As Handelman was saying, the land is removing 25% of the fossil fuel emission every year, and the ocean is cleaning another 25%. And still, we have very large uncertainty, in particular in tropical countries that have not submitted regular inventories so far, at least for most of them, in the land carbon budget. And here you see an example of how atmospheric information can help to compare with the official inventories, which are the black dots. Basically, we found in this study that using atmospheric data over the last 3 decades shows that Northern Hemisphere countries, including the EU, seem to have larger CO2 uptake than what is estimated by the official inventory in the air pollution sector. And on the other hand, there is more sources seen by the atmosphere in many tropical countries. So we do have to understand the reason of these differences, but unfortunately, the current atmospheric approach is only valid for very large countries, and it doesn't allow us to separate the different subsectors of the AFOLU. So next slide, please, is showing that AFOLU is not just a story of top-down monitoring, but it's also a story of using satellite data that are measuring the land surface. In particular, we need long time series. And here, for instance, we found that contrary to the so-called bookkeeping models, which are used in all the global carbon budget assessment and by the IPCC, when you look at the Landsat recent history of deforestation over the past 20 years, multiplying the forest loss area by biomass density, we discovered that unlike assessment that say, oh, the carbon fraction is constant or it's slightly decreasing because the land use is stable, in fact, land use emissions do not seem stable at all. They seem to have doubled in the last 10 years compared to the previous 10 years in the tropics because of small-scale disturbance, forestry, conversion to plantation, etc. So definitely long time series of well-calibrated information on the land for biomass and land cover change are extremely important to track the progress of countries in the AFOLU sector. The last slide is about emerging data set, because in many countries you have no forest because they have trees, but the trees are too sparse to form a forest. And using here very high resolution data from Worldview, it's data which are 0.5 meter resolution. This study has been able to map the crown area and also the height and the carbon content of every tree from Senegal to Djibouti. We counted with a deep learning algorithm no less than 10 billion of trees, and we found that they contain a large amount of carbon for the Sahelian countries, which is completely discounted from inventories, and they also offer a large number of climate services, in particular for agroforestry and the green wall barrier. And unfortunately, those trees have failed essentially beyond the detection limit of current coarse or moderate resolution satellite. It's not only in Africa, but the next slide, which is my last slide, there is also a lot of trees outside forest in Europe. In this study, we used aerial photographs instead of satellite data to map every tree in Denmark, and we found that about 20% of the trees of Denmark were not part of forests. They are part of gardens, roadsides, parks, etc. And the deep learning model we applied for Denmark also helped us to count all the trees in Finland. And definitely, if we want to get a better idea of how much carbon is in the trees, how many trees are outside the forest, I believe that we would need in support of the Green Deal, in particular for urban areas, a very high-resolution data set that allow us to count all the trees, the carbon, and the climate services that they provide. With that, I will stop. It's not the original set of slides. It's not the latest set of slides, but I think it's fine. Thank you very much.
Thank you, Philippe. Thank you. That was excellent. You showed us so much very pertinent data for CO2 like greenhouse gas monitoring. I should just say that we will come back a little bit to methane monitoring. We will have a representative in the panel discussion at the end of today talking or representing the International Methane Emissions Observatory that DG Energy are running with the UNEP, the United Nations Environment Programme. So that connects directly with your talk. It was rather unsettling for me to see your chart that showed the discrepancy between the nationally determined commitments and the path that we really need to follow to reach the goals of the IPCC and the UNFCCC. But there we are. That was very, very pertinent illustration in one of your slides. Okay, so the question and answers with participants, please go to Slido and write your questions there, and we will be able to come to some of those after the next speaker. So within this session on climate, we will now hear about the relevance of Copernicus data for the work of DG Climate Action, and this is René Kolditz. Please, René, it's over to you.
Thank you. Thank you very much. Do you have my presentation or should I put it up?
Normally it should be coming up.
Okay.
Just leave it a second.
All right, then I will start with speaking. So my previous speakers have talked a little bit about the possibilities, let's say also from emission monitoring from space. I will more focus on the existing, the proposed, and also the forthcoming elements where Copernicus will play a role for climate. The next slide, please. And the next slide, please. So I will start with one slide here, giving you a little bit about an overview of the existing climate policies where Copernicus is specifically mentioned. If I'm not completely wrong, LULUCF regulation might have been the first one, where we specifically mentioned the role of Copernicus for also its implementation. I will not go much deeper in here, just to mention that for LULUCF, and also that is replicated then in the governance regulation, the importance of Copernicus lies predominantly in the land monitoring service, and to this end, in the pan-European component under the Corinne land cover, the EEA is working on a so-called LULUCF instance. So this is a quite specific development to enable uptake of elements for LULUCF implementation of the regulation and its monitoring of the emissions on land. Then for the adaptation strategy, there are also several specific mentions of a role of Copernicus. As such, this predominantly links to the climate change service and to some extent also to the emergency monitoring service, and specifically then focuses on resilience, disaster risks, and risk assessment. And there's also strong cooperation between DG Connect and the JRC in this regard under certain Horizon 2020 programs. Next slide, please. In the following couple slides, I will talk a little bit about the Commission's proposal which is currently discussed with co-legislators in the specific fora, so Council and Parliament, towards a revised LULUCF regulation. Let's focus on the bullets to the right, where the proposal makes a quite strong link to Copernicus, because we see here the potential to have lower costs with Earth observation data for monitoring and also for reporting at the end of the day, and thus also for the implementation of a regulation. Likewise, Earth observation can play a role, should play a role in better monitoring of biodiversity-rich and biodiversity and carbon-rich areas. So if I think about forests which store a lot of carbon, they should be very closely monitored in order to not lose that carbon. Next slide, please. I'm not going to walk you through the specific legal elements of the proposed regulation, but there are basically three phases from 2021 to 2025. We keep the accounting system and scope as it is in the existing regulation. In the period 2026 to 2030, there are quite significant changes, because here the Commission has put forward a EU target allocated specifically to member states for its net LULUCF removals to be achieved in 2030. Also, we move away from, let's say, a quite complicated accounting framework with different rules and provisions. The whole system is really put on reported emissions as reported to the EU and FCCC. Therefore, it's a significant simplification. However, this comes along with the requirement for very in-depth and very specific needs for accurate monitoring of what is going on in the land. I will talk about this in the next slides. And finally, in the step towards 2030, the Commission put forward a planning framework to move to a climate neutral land sector. That means the LULUCF net removals would be combined with the emissions from the agriculture sector. That's livestock and fertilizer. I think my previous speaker talked about this before. AFOLU is known to the IPCC community. And here we see that the EU has the potential to reach climate neutrality in that combined land sector by 2035. This is merely a planning framework. There are no specific targets yet. It would require another basic act to be put forward in 2025 based on specific information to be submitted by member states. Next slide, please. So as we have quite more transparent and simplified targets, so a much simpler framework to cope with LULUCF, which is important because then the policy makers also know where to act and what to do. It requires a very specific, or it would require much better monitoring, because as we have ambitious targets, bluntly said, you need to know where to put down your bucks. You need to know your land. You need to know your other policy frameworks, policy requirements in order to understand where are the low-hanging fruits, where to take action on land. And then also to track the action and the effect of the actions in a timely fashion. Because what we see currently is that the national systems are based on ground sample inventories, maybe repeated every 5 to 10 years. So it takes too long in order to track what is going on my land, how effective is my mitigation strategy, and therefore it is quite difficult to know where you actually stand at a given point in time. Of course, this will in the end also or could feed into improved reporting, but the emphasis of the amendment in the LULUCF regulation, which is in fact an amendment to the governance regulation, is focusing very much on a very close, geographically explicit monitoring of what is going on the land. Next slide, please. Next slide, please. Okay, this one. Yeah. to summarize this a little bit, already in the existing regulation, there are quite specific requirements for geographically explicit monitoring. However, it is not just that, also it is quite important to harmonize and standardize this, and this would bring down the currently quite high monitoring costs, because yeah, every inventory you carry out, which is ground-based, has a quite significant cost factor associated with that. So it is absolutely impossible to repeat forest inventories at a national scale every year. Also, we emphasize that the wheel doesn't need to be reinvented. There are specific other policy areas. Let's just mention here the CAP, the Common Agriculture Policy, where spatially explicit, so to say, wall-to-wall monitoring for the agriculture areas which are under payment schemes already undertaken. And these systems are used or audited, because this looks at the compliance, is part of the compliance mechanism under the Common Agriculture Policy. So such information could certainly be used and reused then also for LULUCF in order to monitor areas. I mentioned also that the focus should be quite specifically on carbon-rich areas and protected sites. We will come to this in a second. So in the time frame 21 to 25, we already have requirements for geographically explicit monitoring, which can be geolocated sample sites, but it could also be image data. From 2026 onwards, there is a requirement to do this on all land types, to do it with upgraded emission factors, tiers, and then specific requirements for tier 3 modeling. I will illustrate this in the next slide. Next slide, please. So this slide summarizes a little bit where a monitoring system could stand and which information could be used. So you see information from the Common Agriculture Policy, different cartographic information from remote sensing, of course, also from the Copernicus services. Cadastral information might be necessary when it comes to settlements. There's also information which might come from inventory data, forest inventories, and soil inventory, in order to enrich a monitoring system, because not everything which is going on land can be observed from space, measured from space. It might be possible to extrapolate that information with wall-to-wall information from remote sensing, for instance. And then the regulation puts down quite specific elements on where enhanced monitoring should take place. These are 4 areas which are better illustrated in the next slide. On these 4 areas, tier 3 emission modeling should be undertaken. And here you see this. We would propose to look at high carbon stock land, which is quite important, because this is land also covered under the Renewable Energy Directive, where biomass should not be harvested from for renewable energy. I jump first to the D, also certain zones of high climate risk. So zones where there's a high possibility that natural disturbances may take place, or other natural disasters such as flooding, or which are prone to changes by global warming. And these areas should be closely monitored to avoid such deteriorating effects, or to mitigate those. And the 2 big blocks in the middle, protection and restoration, here I explicitly state the different directives and regulations or legal frameworks which are covered there, because in the legal text this is quite difficult to read because it only mentions the numbers. This gears clearly towards the co-benefits with regards to environment and biodiversity needs. So elements laid out in the biodiversity strategy, or then also to be covered in the forthcoming nature restoration law. So again, the co-benefits between climate and biodiversity would then be substantially strengthened if these areas were to be monitored very closely with geospatially explicit data, geographic data, and tier 3 emission modeling. Next slide, please. I'm coming to the end. This is my last slide, where I would like to highlight a forthcoming initiative. The EU Forest Strategy announced that there should be a legal proposal forthcoming on EU observation, reporting and data collection, and also strategic plans for forests. So in what is meant here is that the current forest monitoring is very much ground-based with national inventories, sampled in, as I mentioned before, 5 to 10 year intervals, certain lag times, possibly also certain misses, very different schemes among the member states. The Commission sees a importance to harmonize this information and provide timely information in order to adjust policies in a timely fashion. When we think, for instance, about natural disturbance, if we think about forest health, timely information and harmonized information across the Union is very important in order to lay out the necessary actions to counter against disturbances, bark beetle infestations or whatever. So here, Earth observation, in particular from the Copernicus program, could play an important role. And the big merit would be to combine the ground sampled information, which have a long history, with remote sensing in order to have harmonized, improved, and timely monitoring systems coherent across the Union. I will not say more, but maybe you watch closely on Have Your Say, because the Commission may soon come forward with a call for evidence and the following subsequent steps, always following the better regulation agenda, so which means public consultations, certain stakeholder meetings, etc. Thank you very much.
Thank you, René. Thank you for a very clear talk from Klima, DG Klima. It just occurred to me, you mentioned the cost of monitoring and that's an issue. Could you expand on that a little? I'm wondering where that cost occurs and who covers those costs in your context, if you don't mind.
Yeah. So the costs are covered by member states. Member states are responsible for the greenhouse gas inventory, and therefore they provide the data. They also need to undertake the measurements. Now, I know a specific number for France, which is the forest inventory. I think costs around 10 million euros. I'm not sure. I would need to dig it up if it was a number by year, but we have quoted that number in the Sustainable Carbon Cycles communication, which came out December last year. This is a quite significant cost. Now, however, this is not only for LULUCF. National Forest Inventory serves many purposes. LULUCF is only one part of it, but it is a very big effort, which is required in order to undertake a ground sample based or to repeat ground sample based measurements. And it's done very differently across the member states with different cycles and also with different strategies, whether they have rolling cycles, so they update 10 to 20% of their data per year, or whether they do a once in 5 or 1 in 10 year complete assessment over the entire territory. Germany does the latter, for instance. And we believe that these costs could be brought down by bringing remote sensing information in.
Right. Yes. Yeah. Thank you. Thank you again, René, for your talk and the answer just now. We have noted that we have a number of questions for Philippe, who spoke a minute ago in this session. He's offline at the minute, but he will respond later. Maybe we can field those questions also during the final session of the day, or otherwise he will answer in writing afterwards. Right, so we are at 2:15, and we're moving to the session devoted to energy. we have 3 speakers in this session lined up. And first of our speakers on energy is Gilles Lissano. Gilles is working, I believe, in 2 contexts, Vortex and Climate Scale, and he's founding partner of Climate Scale and also partner of Vortex. So Gilles, if you are ready, please go ahead.
Thank you very much for the introduction and for the opportunity to share with all the audience how Copernicus data has become really really fundamental in a particular area like the wind resource analysis. So that is a crucial element when developing wind farms. My objective on my presentation is to give an idea of how the Copernicus data is employed now, and also to provide some insights or some ideas on how the use of Copernicus data and similar data as well is needed for the scaling of the wind industry in the next years and decades. So if you can put my slides, I'm gonna go through them. Okay, thank you. So this is the agenda for this 10 minutes. Is basically show you how we use Reanalysis, how we add a value of Reanalysis. Reanalysis is basically the main data set that is employed by the wind industry. So there are other data that come from Copernicus that are also relevant, but I'm going to focus on the use of the Reanalysis. Then how I will also show you how the implementation and the use of the Reanalysis has evolved over the time, and also, as I said, show some ideas about the future, and then a few comments just to finalize my talk with some message to everyone. So next slide, please. So how Reanalysis is employed? Well, we have before a very interesting presentation that shows what is available on the shop of the Copernicus data service by Samantha. And here what I'm going to show is how this data that comes from ECNWF, for instance, like the ERA 5 Reanalysis, is fed into a service like the one that is provided by Vortex to add value and to, at the end, to finalize the process, the modeling process, to output information in the way that users from a particular sector, like the wind industry and wind analysts, can work directly with this data in their analysis. So going from the global reanalysis, we use a downscaling engine. In our case, we use a weather model that is called WRF. Other options, obviously, that we employ in Vortex, and then we serve all the data. Once we have the Reanalysis, increase the resolution and output the data in very specific format for very specific metrics that are really designed for the wind resource analysis, for energy evaluations, and also for the design of the wind farms. We offer this data through an interface. Next slide. And what is really very important is, as I said, the packaging. So from the Reanalysis data, we aim to provide this data in a very easy to use format that at the end, because the resolution and because the metrics and because we have the format that works with the software that is employed by the industry, there is the complete history of usability of the is complete. No? And obviously, here is not only to provide the data, but it's also to work to support the user that needs to respond sometimes questions that are outside the full automatization of the process. So next slide. And what is so in all this process that we go from the Reanalysis, that is a global data set that allow us to reconstruct wind resource, wind climate across any location. What is the added value in all this process was basically is to increase the resolution. So we managed to, from the Reanalysis, to reach the resolution that are meaningful for for the users in the wind industry. So resolutions where we start to see the wind farms, so hundreds of meters, how we derive the specific variables like not only wind speed and wind direction, but shear, stability, different levels that can be adapted to the hoop height of the wind turbine, turbulence, etc. And then obviously it's very important that at the end of the analysis and the process that we do, based on the analysis is verified by the industry, so that our data and similar data are continuously being evaluated by the users using their own data. It's very important as well that we talk the same language. So there's the climate information, and then there is the industry translation services. That is what we do. And at the end, it's also very important that we are able to integrate all this data in the tools that the user from the industry has to, for instance, to run their energy analysis. So it's important that at the end, the format and the variables that we obtain can directly be plugged, and then the end user, a wind analyst in our case, they can just plug a wind farm layout, a power curve, and then go the process and provide the energy analysis for instance, to assess the feasibility of one project. Next slide. So this is an example of, well, this is just basically is over the life cycle of a wind farm from the early stage where developers are deciding with locations to the wind farm in operations when there are other needs of information, how using reanalysis can be very useful to support, in our case, and to derive different products that are adapted to different needs of the wind farm design and energy analysis that goes from resource assessment, icing conditions, extreme events, spatial interpolation, long-term reconstruction, site assessment, turbulence, stability, and even, well, this is another product that is outside from the reanalysis, but is forecasting that is also, that is really important. So next slide. So here are examples of real applications. For instance, on the top here, what you see there is the wind resource, or the wind speed spatial distribution across our real wind farm. We use ERA 5 to drive our downscaling. And on the right, what you have is another project that is run by Climate Scale. It is a sister company of Vortex, that we use again ERA 5 to calibrate and to downscale statistically CMIP 5 and CMIP 6 projections to provide assessment of changes in the future according to different scenarios. So this is something that now there is an emerging demand of information that assess the hazard, for instance, the change on wind resources or wind speed. And this information now is demanded, for instance, especially because the European taxonomy is there, and most of the projects that now are funded required to disclose or to assess the impact according to the different hazards related to climate change. So here we have two examples of how the industry use the analysis and other data that are provided by Copernicus. These data obviously are improved and downstream by people like us, the tech companies that add value for specific values. And at the end, we have products that are really, really actionable information to respond to specific needs. Next slide. So now I'm gonna look just very quickly how I see the future of the demand of information from the wind industry. I want to take an example, an idea that was I saw in a presentation by Arribas in forum about artificial intelligence and water and climate. So I took the same idea, so just basically to try to map how things are evolving on time and which is the return that we get. So next slide. So if we see the past story of the reanalysis, so we see different products that has been developed over time, and it's on the third generations where obviously the reanalysis has been really employed by the industry. Next slide. So it's after a period that the reanalysis were more or less known by the community, more or less trust for use. There was like a step change especially when the latest reanalysis product, and in particular RERA 5, has been available, and this was at the same time the time that project like us, which add value on top of the reanalysis, has been very useful to disseminate the information that we can get from the reanalysis. So now we see that with the reanalysis and the downscaling, the industry is really has already adopted the use of information for decision making. So for feasibility analysis that requires bankability, so the requirement. So and this has been also forced by a global market, because of the century it was not such a global market, but over the last 10, 15 years, the market of the industry has grown quite, not only in Europe or North America, but in every location, every country of the world has a wind energy program, almost everyone. Also because there was a demand of better information to respond to more complex projects, because we are in regions where the complexity of the atmosphere, flow, mesoscale interactions, terrain, etc., involved forest, cannot be represented only by simple models, but need something much more specific. And how we see the future. So if you go to the next slide, please. We see, or this is how I see it myself, is we are again in a moment of fermentation, where we have something that is working very well. It is RERA 5 and scaling, but there is a new demand. If you go to the next slide, I just suggested what are the demand that we need to respond with the new data that is going to be developed thanks to Copernicus, and obviously. So we have, especially the offshore market is becoming global. It's not only something that is North Sea and Baltic Sea and Irish Sea. It's everywhere, especially because floating technology is becoming a reality. Meta-ocean information is really important to support offshore design. Machines, the wind turbines are becoming really, really huge, and so they are more complex. So we need to understand much more better what is the turbulence that these machines are going to suffer. We need information with broader data in new regions. So far, we need to improve what we have, and so on, extreme conditions, and the use of the information in the time domain, because now we are working towards the digitalization of all the processes in the wind farm. So this is the project at the moment where we are here, where we need to adapt and integrate solutions like what could be the next new reanalysis. I put RERA 6. I'm not sure if RERA 6 is the name. And this is what is the demand of that we expect to cover. And then if you go to the next slide, this demand is going to be covered obviously with more meteorological modeling, weather models, but what is very important is how we merge all the sources of information we have. And this is basically what many teams, groups, development, research institutions are trying to do, is to integrate this through, for instance, this ecosystem of artificial intelligence technologies, however you want. But this is basically what we are moving towards, to take the best of the observation, to take the best of the reanalysis, to get very high resolution data thanks to downscaling, and merge together to respond to the demand of complex systems that we are. So to end my presentation today, so in the next slide, is just to remind you that there is a clear return in reducing the bias and uncertainty. And this is something that we have seen over the past. 20 years ago, the uncertainty that we got from our model data was much more higher than the one we have now. And then in this slide, I just put some numbers that I took from the IRENA and from the International Energy Agency report. This is just numbers. Take it with care. It's not need. It's more out of the envelope. I don't want to compromise to this because it's very project specific. But to give you an idea that the return is really clear, and this, when you reduce the uncertainty of a project, of the assessment of the energy of the project, there is a direct impact on the horizon. And just to end my slides, I just wanted to finalize, and this is the last slide, please. To just remember, now that we are here and there are people from Copernicus and the commission that is we as an industry, wind industry, we relied on products like the Reanalysis, and so we can tell you that there are many reasons to keep supporting the Reanalysis development. So thank you very much, and maybe there is a next slide, but this is the end slide.
Thank you, Jill. Thank you, Jill, for this very powerful illustration of the value of Reanalysis and ERA 5 in particular in your sector, wind energy sector. So very much appreciated. So thanks a lot for that, Jill.
Thank you.
If there are questions, they will be on Slido. So appreciate if you, as a speaker, could have a look at those and possibly answer those in writing if you can. Right, our second speaker that we will move on to just now is Marion Schröder-Homscheit. And Marion is a scientist at DLR, the German Space Agency. So Marion, please.
Thank you very much. I assume you understand me very well, and it's my pleasure to tell you today a bit on the Copernicus Atmosphere Monitoring Service and how we support now for many years the solar energy sector. Next slide, please. So first, I would like to open the floor on what's really the role of solar energy in our energy transition system. Some people, mainly the general audience, have this idea, okay, we have photovoltaics, we put it on our rooftops, and that makes a bit of electricity, and that's it. But that's not the whole story. I mean, we are really facing a very, very large energy transition in front of us. I mean, it's power, heat, and transportation sectors, and also fossil-free chemistry sector, and solar energy, as we see, decarbonization is electrification. So we need a lot of solar and also, of course, wind energy. And we use it then, of course, to make electricity, but also to keep it at heat in storages to produce electricity after sunset, or to use it directly in heating systems, or think about all the chemistry area, the hydrogen economy we are facing in future, or the basic chemicals for many industrial sectors, or we just discussing, I think, heavily in recent weeks, fertilizer production, how that will be in future. So we go for the next slide, this white field. We always have three main user roles here. We have investors. Investors want to know, where do I place my power plant? Is my investment worth doing it? But then we have a second role of users here, and that's the engineering teams. They want to have very realistic data, very detailed data to make an optimum engineering decision, to find a cost-effective solution. And as I already mentioned, decarbonization means electrification. So the grid operator is always involved. The power system is affected, whatever, by what we do here and what we change. So again, we need grid extension and we need an optimum one. Again, this asks for realistic data on solar energy production in future. So next slide, please. And solar technologies, as I said, it's not just the rooftop solar you see on here on one image. It's large scale, it's utility scale, it's tracked and concentrating technologies, it's large scale photovoltaics. All these different technologies are used in the world and in different locations. These requirements, again, for data is, first of all, where's radiation available and how much. At the beginning, we start typically with requests for annual or monthly sums, but that's only early planning stages. So it's kind of a solar map or a solar atlas. That's the first information only. What we really need and what comes then also therefore providing is a time series and the detailed information on variability to solve these point of system storage and grid design. We, of course, have citizens here in Europe who want to have the information, but more it's used by companies, and they are acting on a worldwide scale for their businesses. So they want like to have one single data shop where they can get worldwide information. And I think it's also our own interest that we have worldwide access to such data to facilitate the energy transition, which knowing how far we are from our Paris Agreement goals, it's our interest to have a very fast transition around the world. Also, I'd like to mention that a lot of users are doing then afterwards data fusion processes. Either they couple with forecasts or with any other data sources, and that's really, really surprising how large the applications are, how much data fusion is used, and that's the wide range of users which we have in CAMS. So next slide, please. We are answering to that request for solar radiation at the surface that we have to couple information on the clouds and on the aerosols. These are the two main factors doing scattering and absorption inside the atmosphere. So at the end, we would use by that the radiation at the ground, or we change it from direct radiation to diffuse radiation. And depending on the solar technologies, they are sensitive on the direct or diffuse to direct ratio. So we go to the next slide, please. More in detail, we take the meteorological satellites, the geostationary satellites, to know about the cloud patterns, and we take from the CAMS the aerosol and water vapor and ozone concentrations, which again is made with a lot of the satellite capacities as incoming data into the modeling. We are data assimilation, so we should have a double satellite capacity view here. Coupling all that in fast radiative transfer models results then in the radiation at the surface, and the main focus is really on time series. So you see here an example for a time series. Next slide, please. So these time series, depending on the technologies people want to apply on the solar sector, they're interested in global diffuse direct or even direct normal radiation on a normal plane. And we're going back to 2004, and depending on user application, they gather data as they wish, from 1 minute temporal resolution up to 1 month's aggregated information. And you have seen it's a lot of input data which we are coupling, and you can imagine each input data set has its own spatial and temporal resolution, and there's something to say in detail about how to combine them optimally. That we all solve for the users. At the end, the user gives the latitude, longitude, and at any point within the field of the view of the satellites, we can then process on the fly, on request, with the most recent version of the algorithm, the data for the users. And then that's taken currently, we see about 80,000 requests per quarter. Typically, that's to some extent from private citizens, but mainly it's from downstream service providers, from information brokers, from companies providing site auditing. They take it as input data and couple it with couple it into daily business practices. We also provide a gridded data set on continental scale. That's mainly for energy system modelers who want to have really one data set over the whole area. You could generate, by assessing several time series, you could generate also a gridded data set for your local neighborhood if you wish in a very high resolution. People do actually use this functionality and create their own grids all the time. Okay, next slide, please. So one challenge which we're currently looking into is going global. We have now really nice meteorological satellites around the Earth, watching the different parts, which have capabilities like our Meteosat second generation started having in 2004. We have them now in Asia, Australia, the Americas. So we're going step by step to the other satellite platforms. We're currently extending towards Asia and Australia, and we have test mode running. Will become operational later this year. Okay, next slide, please. Now let's talk about an example you may have seen. I'm working at the Institute of Networked Energy Systems in the meanwhile, not in the space program at DLR anymore, more in the energy program now. So I've just brought you an example from my colleagues next door. That's a local neighborhood in Oldenburg, our hometown. And you see the energy demand, which is low or high, colored here in different buildings over the day. And sometime during the afternoon, evening, you will also see the streetlights. Now here it is. And of course, that overall sums, if you please click once more, it's a small animation, that sums up to, oops, no, it's jumping. Okay, perhaps we go one more. One click more to the next slide. No, we're going. Yes, and if that's okay. So you see aggregated. No, we are jumping obviously the animation. Go just one slide ahead. Next slide. So I would like to have the next one. Good. So you have seen we have over time of the day different demand patterns and also different production patterns, of course. And that's what we are now coupling to C3S and CAMS output. So ERA5, what we heard again for wind. We also do this. It's a very nice data set for wind. And the CAMS radiation to couple that with the PV-lib, which is an open source library for photovoltaic systems. And we couple with airborne data. Where do we have the solar systems in our town? And if you couple all that together, then you get this simulation, what you have seen on the previous slide as an animation. And of course, that allows you for all kind of local grid planning, e-mobility planning, storage planning, and all those questions which we have in the energy system analysis. So next slide, please. So let me summarize what we have seen. We have seen the CAMS radiation services provide solar radiation at the point of your interest. It's a time series service. You may choose the different temporal resolutions. And we solve the tricky issue of all the spatial temporal interpolation of the geodata handling. And it's an on-the-fly processing in the cloud for you to make always the most recent and best data we have available. And what really I think is very Copernicus-like is really that we are very open on all the input data we use. If you click on the expert mode, you get the radiation, what you want, but also all input data. So it's really traceable also for the users and those who do kind of machine learning or any kind of training or post-processing correction. They really get all the information, and it's very open, and not just a data set, which you have no idea how good it is. We also do very extensive quality control reporting. And by that, it's not just providing the data, but providing the data with this auxiliary information is key for success. Yeah, as I've shown you, the usage includes questions like optimum location costs and investment security, but also security of electricity supply and grid operations, and all kind of detailed questions on storage planning, all kind of engineering details. And it's coupled very often to nowcasting and forecasting, for example, for trading applications. Yeah, I think the next slide has more housekeeping information, contact details, and the scientific references behind the support address. So you may contact us at any time when we are happy. Yeah, to answer further questions on Slido or later on via that emails.
Thank you, Marianne. Thank you so much. There's another very, very good example of the use of Copernicus data. In this case, from the Copernicus Atmospheric Monitoring Service for the solar data. So yeah, we will move to our final speaker before coffee break, and that's Laurent Dubu. Laurent is Senior Scientist for Weather and Climate Applications with RTE, and RTE is a French transmission system operator. Welcome, Laurent, and please go ahead.
Good afternoon, everyone, and thank you, Eric, for the introduction. And apologies in advance, as I may be coughing or snoozing as I caught a cold yesterday. Hopefully, it will be okay for the next 10 minutes. So we can move to the next slide, please. Yeah, if we can have the next one. Yeah, so as you may know, the European power network is operated by either national or subnational transmission system operators. In France, we have only one, which is RTE, and we operate a very large network of around 100,000 kilometers of high voltage and very high voltage lines from 63 to 400 kilovolts. France has a very important position in the European system because we are, some kind of a central place, allowing to transmit energy from more geographically isolated regions, like for instance Italy and the Iberian Peninsula, to the rest of the network. Anyway, what is important to keep in mind is that power transmission is really not a national problem. Of course, there are national questions, but it's mainly a European level process that needs to be coordinated among the countries. Next slide, please. Now, of course, to limit the impacts of climate change, the EU Green Deal has set ambitious plans to achieve climate neutrality by 2050. And of course, the decarbonation of the energy sector is crucial to fit these targets. Together with energy consumption limitations and energy efficiency improvements, the electrification of uses is key to meet these targets. This will be possible only, of course, if electricity is produced in a cleaner way, based on low emission technologies, and among those technologies, of course, renewable energy sources, among which wind and solar energy will play really an important role. Next slide, please. So in brief, we can say that new energy systems will be more and more complex than those of the 20th century were. There will be more generation from geographically distributed sources, different consumption patterns with, for instance, the use of heat pumps and the generalization of electric vehicles that will really change the pattern of the consumption. And many other new technologies and different constraints, because the constraint of a classical rotating alternator are not the same as the power electronics of a wind farm, for instance. And all this will make the design, the optimization, and the operation of power systems more and more complex. And of course, this clean energy path has to be addressed at the EU level in a coordinated way. And on top of the national TSOs, of course, ENTSO-E, which is the European network of the transmission system operators for electricity, really has a key role to play here. Next slide, please. So you all know that the power network and the energy sector in general is really dependent on weather and climate at all time scales. This concerns mainly two aspects for power networks. So the first one is that the assets themselves have to face climate variability and weather events, including both normal conditions, but also extreme events. And here we are talking about network resilience. And on the other side, the operation of the power network is also dependent on weather and climate variability, from real time to seasons ahead. And that's what we call supply-demand balance or resource adequacy assessment, by which we need to ensure that the supply meets the demand for every customer at every time step. The net zero targets and the Green Deal, as I said, mean electrification of uses, energy efficiency improvements, and increasing the share of clean energy generation. So climate change and the evolution of energy mixes both will make energy systems even more dependent on weather and climate variability, and their future evolution as well. And climate change really needs to be taken into account in all aspects of the power system, and especially for the design and the operation of power networks, from asset management to resource adequacy studies. And of course, on the shorter term, progress in forecast will be a key ingredient in the efficient integration of renewable energy sources. That's to say that we need to, for instance, reduce the forecasting errors for wind speed and solar radiation, so that the integration of our wind and solar energy on the power networks today is already facilitated. Next slide, please. I now give you a few examples of climate services usage at RTE, starting with the network resilience problem. So we have currently a project that we are running, which is called Resilience, that aims at estimating the impact of heat waves, droughts, and floods, both from rivers and marine submersion, on the main network assets, which are overhead lines, underground lines, pylons, and power stations. The goal is to identify the threatened elements of the network, to adapt them to future anticipated conditions, and also to safely dimension future assets so that they are able to operate safely under future conditions. For this, we use dedicated climate simulations provided by Meteo France, one national Met service. These datasets include several sets of 200 climate years, both for the present climate and for the future, so 2050. But we are also considering other sources of information, like the more general DRIAS project from Meteo France as well, based on Eurocodex. And of course, we're also considering information from C3S, especially the information provided by the sectoral information system for the energy sector that Samantha mentioned earlier today. Next slide, please. The second example of climate services use at RTE is our recently published study, which is called Energy Pathways to 2050. The executive summary in English is available on our website in case you want to have a look. This study aimed at providing an extended analysis of different energy scenarios, so 6 precisely, under different energy consumption pathways to meet the European and French targets to 2050. And the idea of this study was to help the policymakers and decision makers in France to decide what the long-term development of the French power system should be. The complete modeling of the system done with our Antares simulator, which is an open source tool, allowed to take into account different climate datasets. So one for the years 2000 and 2 different ones for 2050 with ACPs 4.5 and 9.5. And once the model runs, we have access to a lot of information, which allow to make a comprehensive analysis on the technical, economic, environmental, and societal aspects and outcomes of the model. So we used dedicated climate simulations from Meteo France for that exercise, because when it started, the C3S offer was not that developed. It was more than 3 years ago. But of course, recently we have compared these simulations with the C3S offer and more generally the Eurocodex simulations, just to ensure that things are let's say relevant with each other. And of course, the future developments we will do will take into account multi-modeling aspects, and we will consider using more deeply C3S information. The third example I'd like to give on the next slide concerns our seasonal outlooks, which are done at the national scale, but also so in other countries as well, and at the NCOE level. Sorry, the slide is in French, but it's not a matter, I think. So basically, the idea of these studies is to study the adequacy over the coming season. So we do that every autumn and every spring for the following winter and summer. Until very recently, these kind of exercises were done using only climatological information or Reanalysis information. But considering the progress in subseasonal to seasonal forecasting, we are now developing some tests to include this kind of information in our processes. So far, it's only from a qualitative point of view, but then the next steps will probably include using the numerical outputs from numerical models, so from seasonal forecast, for instance, in our simulations in order to better assess the adequacy over the coming months. Next slide, please. So you will probably have understood that I'm really convinced that energy studies should be done using the best available information. And I think one important point is that, especially when it comes to public decisions and long-term investments and so on, there should be a common ground, common basis for climate information, which should be available to everyone. And I think that Copernicus approach is very good in that sense, because it provides good quality data, the state of the art, which have been validated, quality assessed, and so on, and which are equally accessible to everyone. That can be a very good basis and a good set of assumptions for any study about the power sector and the power networks in particular. I can mention, because it's no public, that at ENSOE level, it was recently decided to move from data sets based on Reanalysis to climate projections in the so-called Pan-European Climate Database, which is in essence the data set related to climate information that is used for long-term perspective at ENSOE level. So the decision was to work with together with C3S to develop the new version of that dataset, which will take into account climate change and then will be based on climate projections. So this is an ongoing work, and you will certainly hear about it in more details in the future. Basically, the idea is to expand on the current C3S energy service that will be refined and improved to meet specific needs. But the idea is that this very nice service will become even more adapted and tailored to the needs of all the European sector for the energy. Please, next slide. So moving from Reanalysis products to climate projection-based products, of course, would be a major step for many users. Many of them don't really know what it is about, and there's of course a lot of needs for training, communication, collaboration, explanation, and so on. And I personally think that the very strong experience that C3S acquired over the last 5 or 6 years in stakeholder interaction, engagement, and collaboration will be a key element to the success of that undertaking. Next slide, please. So in a few words, if we summarize what are the needs, I would say that for the power sector, the needs are really user-driven. So the developers should really hear the users and what they need and what are their constraints and so on. Then it needs to be science-based, meaning that we need to use state-of-the-art, authoritative and transparent climate data that can be also mentioned as reference to public authorities like the ACER that was mentioned earlier as well. Of course, it includes considerations about the FAIR principle and so on. There are also emerging needs that need to be taken into account. Sometimes the users consider that the progress in providing new variables, for instance, is too slow, but that's something that has greatly improved in the last years, I think. And for instance, we can mention that for the wind power industry, having only 10 meter and 100 meter wind speed is not enough, and there is probably a need for different altitudes information. And also in the future, in the next 4 or 5 years, probably we will need much finer information from a temporal point of view, even for projections, because the electricity markets, which are operating now more or less everywhere at 1 hour time step, will be moving to 15 minutes or even 5 minutes in the future. So there's some need to talk together between the users and the providers to see how we can fit this need. Last but not least, I would say that there's a strong need of homogeneity through the timescales, especially because between the short-term to medium-term forecast and the longer climate predictions, so subsequent to seasonal and further. And also there's a strong need of harmonization across the sectors. And for all those reasons, I think that Copernicus is a very good framework, a very good program to progress all together in this direction. Sorry. And I think you can just put the last slide, but I won't go through it. I think it's obvious from what I've said. And I would like to thank you for your attention.
Thank you, Laurent. It's very interesting. There was, in earlier talks, there was mention of future releases of Reanalysis. ERA 5 is the current one. ERA 6 is the next release. And I wanted to bring up then the question about what are users looking forward to in the future evolution of these Copernicus services. And I think you show that very clearly on your second to last slide, where you listed so unmet needs. And you mentioned higher temporal resolution, higher spatial resolution, better homogeneity and consistency in data. So thanks a lot for that, because that provides all the impetus to keep improving and extend the range of products and qualities. So that concludes the session just now, and we have a short coffee break next. We will start again on time, 3:15, and at 3:15 we will have a session on mobility and zero pollution. So, okay, we do a quick coffee break now and see you again in 10 minutes.